This question asks for the conditional expectation of t given t is greater than 1/2. T is some random variable that's described as an exponential random variable with parameter 1 plus theta conditionally on theta. Theta itself is a random variable which is a 0.01 Poisson random variable. Now this conditioning, t greater than 1/2, is conditioning on a simple event, which we maybe call b. b is equal to t greater than 1/2. And so we think of this conditioning as changing the probability measure. And so we're really looking at probability distribution of t given this event b, t is greater than 1/2. This just changes the probability distribution of our non-random variable t. So first what we could do is look at a conditional likelihood, which would be the probability that t is greater than little t given t is greater than 1/2 as little t varies. This is a reliability corresponding to this conditional probability. And then we know the expectation of a random variable is the integral of the reliability if that random variable is non-negative. Well, t is non-negative, so we know that the conditional expectation of t, given that t is greater than 1/2, is the integral from 0 to infinity of the conditional probability t being greater than little t, given that t is greater than 1/2, i.e. the integral of this conditional reliability. Well, since these are both simple events, so we could think of t being greater than little t as A and t being greater than 1/2 as B. So elementary conditional probability says that that is equal to the probability of AB, which is the probability that t is greater than little t and t is greater than 1/2, over the probability of B, which is the probability that t is greater than 1/2. The top part, which considers the probability that t is greater than little t and t is greater than 1/2. Well, that's the same as the probability that t is greater than the maximum of little t and 1/2. And so we can divide this integral from 0 to infinity into two parts. That going up to 1/2, where t being greater than 1/2 is the more restrictive condition. So the probability that t is greater than 1/2 maximum little t is just the probability that t is greater than 1/2, and the integral from 1/2 to infinity, where t being greater than little t is more restrictive, and so the probability that t is greater than little t and t is greater than 1/2 is just the probability that t is greater than little t. Now for the first integral, we have the integral from 0 to 1/2 of the probability that t is greater than 1/2 over the probability that t is greater than 1/2. Well, there's no little t in that integral, so that could just come out, and we're left with 1/2 times the probability that t is greater than 1/2 over the probability that t is greater than 1/2, which of course is just 1/2. The second integral is a little more complicated. It is the integral from 1/2 up to infinity of the probability that t is greater than little t over the probability that t is greater than 1/2. Now we would ideally like to use a memoryless property. However, that does not hold immediately because t is only exponential when conditioned upon theta. However, we can partition over theta so that we know the value of theta, and so we could write the probability that t is greater than little t as the sum from I equals 0 up to infinity of the probability that t is greater than little t given theta is equal to I times the probability that theta is equal to I. We know that theta is Poisson, and so it has an alpha bit that's equal to the non-negative integers, i.e. 0 up to infinity. And then we know that t, given theta is equal to I, is I plus 1 exponential. And so we can substitute in that conditional reliability just being the reliability of an I plus 1 exponential, which is e to the minus I plus 1 t. And then we can also substitute in the probability that theta is equal to I. Well, that's a Poisson distribution as we were given with parameter 0.01, which is 1 over 100. So that's equal to e to the minus 1 over 100, 1 over 100 to the I over I factorial. And we simplify that just by bringing out terms to get e to the minus 1 over 100 minus t, and then that is times the summation I equals 0 to infinity of e to the minus t over 100 to the I all over I factorial. And so we recognize this last part as a power series expansion of an exponential. It in fact is the exponential of e to the minus t of all over 100. And so we can write this then out as e to the minus 1 over 100 minus t times the exponential, or e, to the e to the minus t over 100. That sounds complicated, but that's what it is. This type of form is not that unexpected when you have Poisson type distributions. And now we can simplify. So the probability that t is greater than little t over the probability that t is greater than 1/2 is e to the 1/2 minus t times the exponential of e to the minus t over 100, all over the exponential of e to the minus 1/2 over 100. Moreover, the antiderivative of e to the minus t times the exponential of e to the minus t is equal to minus the exponential of e to the minus t. Scaling by 100, we find using this antiderivative that the integral from 1/2 to infinity of e to the minus t over 100, the exponential of e to the minus t over 100, is equal to minus the exponential of e to the minus t over 100 evaluated positively at infinity and negatively at 1/2. This simply then is the exponential of e to the minus 1/2 over 100 minus 1. So putting everything together, the conditional expectation of t given t is greater than 1/2 is equal to 1/2 from that first integral that we evaluated first, plus 100 e to the 1/2 times the exponential of e to the minus 1/2 over 100 minus 1 all over the exponential of e to the minus 1/2 over 100. Simplifying, that's equal to 1/2 plus 100 e to the 1/2 times 1 minus the exponential of minus e to the minus 1/2 over 100. Substituting this into a calculator, we find that this is approximately 1.49697.